Okay, so we have today we have Michael Balch returning to give us a talk. Michael is the technical lead at Alexandria Validation Consulting. Has 12 years of experience as a research practitioner specializing in uncertainty quantification, and has previous experience working on applications spanning engineering, medicine, defense, and finance. Today, he's going to give us a talk on beyond false confidence. So, yeah, Michael, take it away.
Okay. Let me share screen. Yeah. Oh, wait. Share. All right, sharing screen. And is everybody getting that full screen?
Yeah.
Yeah.
All right, wrong slide. All right, here we go. All right, so this is going to be 3 mini presentations in one. Just getting into some of the, weird basic issues that still crop up even in the realm of, valid statistical inference via confidence curves. So yeah, today we do the weird stuff. The 3 topics I'm going to go through are what I like to call hyper-incoherence, likelihood nonconformity, and a little phenomenon I would call fluke confidence. Not false confidence, fluke confidence. And it's kind of the mirror image of false confidence. But before I start this, I just want to say you're going to see a lot of weird stuff in this presentation. But I want to emphasize none of this actually poses like a danger. Like all these things are counterintuitive, but none of it poses the danger the way that the false confidence phenomenon does. But it's still issues we'd like to control, and at least 2 of these issues, I think, hint at additional constraints we should have in statistical theory. I'm just not entirely sure how to formulate those constraints yet. Hence the presentation. I'm hoping maybe I can get some other people to work on it too. I haven't given up on this. I'm just trying to recruit. All right, so we'll just start with the perfunctory review slides, same as last time, where the goal here, we're in the realm of statistical inference. We're usually inferring a fixed parameter inferred from random data. Theta is your parameter, X is your observable. There are rare cases where you have like an aleatory prior for theta. We're going to put those to the side. This is fixed parameter, random data. There are the 2 traditional approaches, Bayesian and frequentist. They've both got their strengths and weaknesses, and basically the strengths of the Bayesian approach are that it's, very straightforward. You've got a formula for doing everything, and you get very nuanced belief functions. The weakness is that those belief assignments aren't very reliable. Frequentist inference is the mirror of that. You've got very stodgy, stilted, limited inferential statements that you think could be more information rich. And but everything's reliable, and you've got some well-founded additional properties like efficiency. So we want the best of both worlds, basically, and we're trying to get it via confidence curves. So we've been through the false confidence theorem a million times. You've got, again, the presentation for that is from Ryan Martin a month ago. But basically, it's this thing you get with purely additive belief functions, where you get a lot of belief consistently assigned to false hypotheses, and it's generally a big safety problem. This is a big issue in satellite conjunction analysis, which is where I encountered it. So that has motivated me to move towards confidence curves. Lots of names. I've called them constant confidence structures in the past. Ryan Martin calls them inferential models. There's basically a possibility distribution where all the little slices are confidence regions. And lots of ways to derive these. You can take a confidence distribution and do a random to fuzzy transform. You can do a structural model, and sorry, that's a typo. That's not last week's presentation. That was Ryan's presentation last month. And of course, my preference is to derive confidence curves via a test statistic. And more specifically, I usually like to use a likelihood adjacent test statistic, something like relative likelihood or likelihood ratio, or sometimes even a Bayesian posterior, which is nice and perverse, but sometimes gets you good results. So for those of you who get, this is how confidence curves work, how you read belief and plausibility. I'm not going to sit here and read the equations, but you know, it's a very possibilistic logic. So, and you guys, most of you work with Scott, so I assume you already know how possibility theory works. But what's special about confidence curves is
they probably won't know that.
They don't know that?
Probably not.
Okay, well then let's go back a slide. So the logic of possibility theory, in a nutshell, is a process of elimination. You're looking at the main object of a possibility distribution as this pointwise plausibility function. And the plausibility of a set is the maximum pointwise plausibility. So you look at all the points on it and say, what's the highest pointwise plausibility? That's the plausibility of the set. And then confidence or belief is just 1 minus the plausibility of the negation of that set. So you can really only accrue positive belief or confidence to sets that are 100% plausible. So this kind of gives you a very focused inference. It's highly non-additive, very reserved, and that's what allows it or enables this framework to give us reliable inference, i.e. Martin-Liu valid inference. The idea behind, so that's what makes confidence curve different from any other possibility distribution, is that it satisfies the Martin-Liu validity criterion. Which is to say, okay, for each data, for each draw of the data, you would get a different confidence curve. You know, the confidence curve depends on the data. And the Martin-Liu validity criterion stipulates that the plausibility of the true perimeter value over repeated sampling of the data, you'll be, you know, building different confidence structures for each, different confidence curves for each draw of the data. And for each of those confidence curves, you get a, you know, plausibility at the true parameter value. Martin-Liu validity says that that plausibility needs to have a uniform distribution over repeated draws of the data. And what that does for you is it guarantees that your belief assignments are going to be reliable. It means that you'll have a very low probability of assigning any false proposition a very high belief value. You know, you don't want to be always assigning the high belief values to false propositions. So it's almost, even though the validity criterion predates the discovery of false confidence by a decade, to my knowledge, or roughly, it's almost tailor-made to say just no false confidence. That's almost the whole point of it, is we don't want to have false confidence. Okay, but today's going to be where we're taking all that for granted. Go see my last presentation and Ryan's presentation if you want more on that. Today, we're going to be talking about other things we like to see in inference, like we might like to see a you know, some sort of relationship between plausibility and likelihood, or even if you don't think you want to see that, intuitively you want to see that. We want efficient belief plausibility assignments, but will that have consequences? And it turns out it does. And we also just want to have intuitive belief and plausibility assignments. Like, it's still within valid inference, within confidence curve, it's still possible to get some, even if you're doing likelihood conformity and all of that, it's still possible to get some really weird belief and plausibility assignments. So we're going to go through all of these 3 issues in this presentation. So like I said, 3 mini presentations, and the first one is called hyperincoherence. So last week, and this is kind of like a follow-up on, not last week, but my last presentation. We talked about, my last presentation was all about trying to get efficient, tight confidence curves on marginal structures. So that has a weird side effect, which is basically we're going to break all the rules and we're going to do it on purpose. Okay, and what am I talking about? So first of all, let's review the idea of incoherence. This is it's a term I really hate. So why am I saying hyperincoherence? We'll come back to that in a second. But it's basically, it's Bayesian speak for any representation of uncertainty that violates the Kolmogorov axioms. So in Bayesian speak, everything we do with confidence curves, everything we do with p-boxes, all that stuff, it's all incoherent because it violates the Kolmogorov axioms. And they've got a bunch of rhetoric around automated decision theory that supports that incoherence terminology, but I've never really encountered a problem where any of that mattered. I'm not particularly interested in AI. I'm a big skeptic of automated decision-making being a desirable or useful thing. But yeah, they're big on it. But okay, so I'm real down on this term incoherence, but I think it's worth maybe acknowledging in the case of efficient inference, because we're going to do something that doesn't just break the Kolmogorov axioms. We're actually aiming to do something that breaks every single axiomatic system, whether it's Dempster-Shafer, creedal set theory, possibility theory, every system that I'm aware of in use has this one property, and not just this one property, there are other properties that flow from this, but it's this very simple intuitive idea that if A is contained in B, if A is contained in B, then B should be at least as plausible as A. And when we do efficient inference, when you remember last week, we were taking all of those, fat structures and squishing them on marginal variables and squishing them down to be tighter to give us better inferences. We're breaking that because what we want is a plausibility on the marginal variable that's less than the plausibility on the original variable space, the filament in original variable space that's equivalent to our value of the marginal variable. And what that means is there are going to be subsets of that filament in the original parameter space that have a higher plausibility than the total filament. So we're going to do some pictures. Let's not get dragged on the equation. So last week was all about these pictures, okay? We first built a joint structure on our parameter space theta, okay? That's what's in black, and we have different methods for doing it. That's why you've got two black lines. But then we wanted something more efficient. We said, hey, we can do better than this. We can get tighter inference on our target variable. So, for difference of means, you got this blue line, and for ratio of normal means, you got this funky blue line, and they're much lower. Basically, when you think tighter structure, that's equivalent to thinking lower pointwise plausibilities. And lower pointwise plausibilities is going to translate into lower measurable plausibilities, okay? So now let's take this to another level of abstraction. Say the marginal variable is on your vertical axis, and your total original parameter space is the plane of this slide, okay? So what I was talking about, so for, excuse me, just a minute. Or a second, rather. Okay, so this is the kind of stuff I was talking about. Our goal is to get efficient inference on, marginal variable. So we're driving down the plausibilities for each value of the marginal variable. So this big set B up here is expressible in terms of marginal variable, and this little guy A is only expressible in terms of theta, or at least it's not expressible in terms of bar phi. So the upshot here is that it's possible, and in fact inevitable, that there are going to be sets A like this that fit inside of B, where even though if you take their plausibilities based on the original confidence curve for theta, the original joint confidence curve, plausibility of B will be greater than that for A. When we squish down that confidence curve for var phi, the corresponding plausibility assignment for B will be less than the plausibility assignment for A. And just to note, and the key to this whole understanding this whole thing is A is not expressible in terms of that, marginal variable. That's where that's gonna be a big deal here in a second. That's the key to this whole thing. So what's the deal with this? Is this just a, what's the word I'm looking for? Is this just a byproduct of doing possibilistic math? Or could we, last week we discussed the fact that you don't have to use possibility theory to get valid inference. It's kind of convenient. It's much more compact to represent, et cetera, et cetera. So could this be a side effect? Is there some other mathematical framework we could use where we would have efficient valid inference and we wouldn't be breaking every axiomatic system we've ever known? And the answer to that question is no. Okay. You can basically work this up as a theorem, and I've got the proof written down somewhere around here. But basically, and maybe some of you can solve this at home if you like, but basically, if you start with the fact that the confidence structure of whatever sort is Martin-Liu on the original parameter is Martin-Liu valid, and you also start with the fact that you've got, your marginal variable and your original parameter space are not a one-to-one function. If this only happens if theta is, say, multidimensional and there's like a continuum of data points that are being mapped to each value of phi. But that's, of course, that's where we care about efficient inference in the first place. Okay, what basically happens is if you're just mapping, if you're taking, if you're just mapping from the confidence curve for phi to the, if you're just mapping from the confidence curve for theta, your original parameter space, to the marginal parameter space, which is what these black lines represent. If you're to do repeated draws of the data, it's going to have a strictly right of uniform distribution, which means there's room for improvement. But what that room for improvement means is if you actually execute on it and improve on it, you're going to end up breaking the rules. You're going to end up having, again, you're going to end up having this happen. Plausibility of B being less than the plausibility of A, even though B contains A. And yeah, like I said, this does translate to measurable sets. Otherwise, we wouldn't bother doing efficient marginalization. And again, I really want to emphasize this isn't an accident. Like the weird thing about it is we're breaking all these rules, but we're not doing it by accident. Like efficient, it's not even really a byproduct. Efficient marginalization is breaking the whole point of efficient marginalization is to get the plausibility of B to be less than the plausibility of A. And so that might sound really bad on its face, but is it actually so bad? Okay, and here's my thinking on this, because this has been sitting in my notes for a while. And of course, I've been hesitant to publish because of the rhetoric. I'm not trying to sandbag our theory while it's in its infancy, but does kind of make sense, like this whole efficient marginalization thing. And the reason I think it makes sense is that questions about any marginal parameter are a strict subset of questions about the original parameter space. You remember how the key to plausibility of B being less than plausibility of A, the key to that is that the plausibility of A isn't expressible in A itself is not expressible in terms of the marginal parameter space. Okay, so there are questions that we can ask about theta that we cannot ask about phi. And basically we're asking phi to carry more, or we're asking theta to carry more information than we're asking phi to carry. So the idea here, the reason this doesn't freak me out and make me abandon the whole framework is that it makes sense to me that a more focused inference is a tighter inference. If you're using, if you're answering fewer questions, then you can focus the data more to answer those questions more completely. Now, another question that's come up to me while contemplating this is, well, why doesn't aleatory uncertainty work like that? And well, there's a big difference between inference and just aleatory uncertainty. Strictly speaking, if you've got a pure aleatory uncertainty with a well-characterized distribution, technically you've got infinite data to do that. You can't really improve on infinite data. Now there's Bayes' rule and refinements of epistemic relevance. That's a whole other kettle of fish. But you can't really make aleatory uncertainty tighter by asking fewer questions because it's already as tight as it can get. And also intervals don't have this property either because they're all 0 or 1. But I think it may still make sense for confidence curves to have this property. Now, there's a whole other question, which is to say, okay, well, we could ditch this, paradox or quasi-paradox, but just never making our marginal inferences more efficient by never going from the black curve to the blue curve. And I think that's garbage because if you actually look at the results for really high dimensional problems where you've got a lot of input variables that have inferential uncertainty, it's not going to be workable. You're going to get these super wide structures if you don't do efficient inference. And everything will be over-engineered to death if you're doing risk analysis on that basis. But in risk analysis, I think doing the sufficient marginalization is warranted because you go into the problem, knowing this is a marginal variable I'm interested in. That's all I'm interested. These are the only questions I'm answering. Let's just get to it. There are other situations where efficient marginal inference does not make sense. For example, in data mining, where the variable that interests you is purely a function of the data. So any reliability claims you might make on the basis of efficient marginal inference will be corrupted by the fact that the marginalization you did was motivated by the actual outcome of the experiment. That's why p-value correction is a thing. So yeah, I think this does not actually keep me up at night. It hasn't for a long time. I think efficient marginal inference is fine as long as you went into the problem knowing that which marginal variables interested you. As long as it's not data, as long as that marginalization choice is not data dependent. If it is, then you should just stick with the original structure on theta and how that maps and gives big fat results. Okay, so that's the first thing. That's hyperincoherence. That one doesn't really actually keep me up at night, and I don't think we actually need to add more rules to in fact, we can't add more rules to the framework. Because again, it's a logical consequence of insisting on reliable inference and efficient. So let's move on. We've got likelihood nonconformity. So this idea came up while I was working on binomial inference, and it also comes up in Poisson inference. So let's talk about just these problems in and of themselves. So binomial inference is where you're inferring the probability of an event. So just to be clear, we've moved on to, this is our second mini presentation. Throw away everything you just heard about hyperincoherence. Now we're talking about likelihood nonconformity. Okay, so binomial inference is inferring the probability of an event based on n trials with k successes, where the event happened. Okay. Now, if you guys have done a little statistics, you should know, hopefully should know, that the standard frequentist answer to binomial inference are the Klopper-Pearson bounds, okay? But they're notoriously over-conservative. So for, I kid you not, 65 years, people have been trying to improve on the two-sided Klopper-Pearson bounds. And the first guy to try to do this was a guy named Stern. And his idea was, hey, let's use just likelihood itself as a test statistic and see what that gets us in terms of if that gets us tighter confidence regions. And it does. But it also gets you confidence regions that aren't always confidence intervals. Okay? And this, in the Stern regions, this is best exemplified when k is close to n or 0, the extreme values of k. So instead of just looking at confidence regions, we work with confidence curves. So we're going to look at all the confidence regions at once. And when you look at it as a confidence curve, this phenomenon shows up as spikes, these weird little spikes. And you've also got them over here. They're just not as extreme. These little spikes where if you zoom in, you can see it's actually coming up, where intuitively it should be going down. And ever since Stern, people have been trying to fix this. People have been trying to find a different test statistic where you don't get these stupid little spikes. Okay, and side note, Poisson inference, very closely related problem, has the same issue. So it turns out getting rid of those spikes is really, really difficult, improvably difficult. And this is where I'd like to plug my latest IJAR paper. I think it's still free. Today's July 22nd. That's the last day it's supposed to be free. So make sure you get there if you want to grab a copy. My author link is on my Twitter, is pinned on my Twitter page. That's probably the easiest place to go get it. And anyway, so that paper goes through how hard this was to do, why it's hard, why nobody could solve it for 65 years, and what the ultimate solution actually looks like. I'm not going to go into those details. I'm just going to show you that yes, it is possible to get an answer to binomial inference without those little spikes. But in peer review, one of the reviewers brought up a question that annoyed me at first, but then it occurred to me, no, it's actually a good question. Are the spikes wrong? People, and I just taken it for granted, people have been trying to get rid of them for a long time. And I mean, come on, like values closer to k over n are just more plausible than values further from k over n. And those spikes are contradicting that. These spikes are saying, no, we're getting further from k over n, but for some reason, this value over here is more plausible than this value over here. But again, stamping my foot about my intuition and the fact that it's a shared intuition, none of that unto itself is an argument. Where does this intuition originate? And I eventually settled that it's probably likelihood. It's probably the fact that we think plausibility should work that way because likelihood works that way, and likelihood kind of is a primitive, uncalibrated plausibility. So this brought up the question is, we're basically expecting the confidence curve for binomial inference to have this unimodal shape. It's going to go up, and then at k over n, or some region around k over n, it's going to be 1. and then it's going to go down. It's going to be unimodal. But do we expect every confidence curve to be unimodal? And the answer is no, we don't actually. This is our old friend from the last presentation, ratio of normal means. And we don't expect this guy to be unimodal because taking, if the bottom in this ratio is close to 0, we kind of expect things to be messed up. Screwy things happen when you divide by 0. But what this thing does do, what this curve does do, is it adheres to the likelihood function. If you look at plausibility as a function of relative likelihood for the ratio of means problem, it's actually a strict one-to-one function. So basically our plausibility contours, they might be doing something that at first blush looks weird, but they're not doing anything that the likelihood isn't doing. Whereas with the original structure due to Stern, and also coincidentally all the other structures for binomial inference that have spikes, they are doing something that's contrary to the likelihood function. Each spike represents a region where plausibility is a negative function, at least temporarily, a negative function, or not temporarily, locally, a negative function of likelihood. And I think that's where the counterintuition originates. And of course, when you throw up the equivalent chart for my clever solution of binomial inference, it does not have that problem. Plausibility is a strictly non-negative function of likelihood. And there are limits on this. I thought through like, okay, so what I'm enforcing here when I say no spikes, we're enforcing a kind of likelihood conformity criterion. How far can we go with that? For example, in ratio of normal means, it's a strict one-to-one function. A lot of stuff involving normal inference, you can get a strict one-to-one function of plausibility to likelihood. But it turns out in binomial inference, you really can't. It's too tight. The problem overall is too tightly constrained to then say, okay, now I want a one-to-one function. These two, so if you look at and this is kind of obvious just looking at the left side and the right side of the structure. So it might help if I go back to the original plot. You see how this has a left, I think we're doing n equals 10, k equals 1. This has a left side and a right side, and they've definitely got different numbers of jumps and whatnot. So clearly, they're not going to be the same function of pointwise plausibility to relative likelihood. They're going to be different functions. But it's at least always, what we've achieved is something that's always has a non-negative relationship to likelihood. And that's about as good as you can do. Again, if you read the paper, you'll find out why this problem is so tightly constrained, why it's really, really hard to get just that far, just to get that non-negative relationship. Okay, so moving on. So that's the other thing. So my big idea here is, my big idea here is that we probably should have some likelihood conformity requirement in the theory of confidence curves. I'm not sure how to formulate it yet, other than to say it's not going to be a super strict requirement. It's going to be there's going to have to be some give on it. It may be some sort of a minimization criteria where you're minimizing the discrepancy between these functions and some target. I really don't know yet. Okay, fluke confidence. This is our third mini presentation. Okay, so bring hyper-incoherence back into your mind. Okay, let's think through the full consequences of hyper-incoherence. Basically, what we found is that if we want efficient inferences on marginal variables, then our structures for different marginal variables will be completely incompatible. And again, that's not just to say, oh, they're going to break the, in probability theory or any of the other frameworks we work with, we expect, hey, we're going to have one coherent representation of this thing. And what we're saying is, no, not if you want efficient marginal inference. You're going to have incompatible representations. So once you've done that, the question is, well, number one, why constrain yourself to possibility theory if you're not actually trying to make one coherent structure for every question you could ask? And number two, why not, just go for the throat? Why not do the most efficient inference you possibly can on every single proposition that you're interested in, just individually? At least in risk analysis, you go in knowing kind of what propositions interest you, my spaceship blowing up or whatever. So why not just do the most efficient inference possible on an indicator function for that proposition? So at least must have been at least a year and a half ago, I decided to go ahead and try it. And this is very strongly analysis to hypothesis testing. So I decided to use a couple closely related test statistics, likelihood ratio and relative likelihood. And so let's be clear about what I mean by those two things, because sometimes the two terms get used interchangeably, but they're actually slightly different. And that'll actually have some structural consequences in the answers we get. So likelihood ratio, the generalization of likelihood ratio from, I'm thinking specifically Neyman-Pearson likelihood ratio from the Neyman-Pearson lemma. It's a big deal in frequentist theory. Go look it up if you don't know it already. But it's renowned for giving you really, really efficient inferences. And there are a lot of ways to generalize it, but I'm going with the simplest here, which is to say likelihood ratio is the maximum likelihood value over A over the maximum likelihood value of not A, A's complement. Relative likelihood is slightly different. It's the maximum likelihood over A, your proposition, divided by just the maximum likelihood period over the whole parameter space. So the whole difference is just these two little subscripts on the maximization. And for both, we're computing plausibility as the plausibility of A as being the probability of having gotten a lower likelihood ratio or relative likelihood than the one you actually got. And of course, belief is just 1 minus plausibility of not A. Yeah, okay. So this has, even though these two test statistics are very similar, it's got, this will actually give you very different mathematical properties for inference. It's weird, you'll get similar inferences, but also a different mathematical structure for those two inferences. Likelihood ratio, and again, I'll have to dig this out. I forget if there are any limits on this proof. I don't think there actually are. Likelihood ratio, let's say, will very often give you a pairwise additive plausibility assignment on A and the complement of A. In other words, belief of A will always be equal to plausibility of A. Now, that doesn't mean we just found our way back to probability theory, okay? What it means is that we're gonna have, if we apply this system to all the propositions that are out there, we'll get pairwise additive for each A and its complement. But then if you start combining different A's that, would add up to each other under probability theory, they will not add up. Like, you're not going to have an overall additive belief function. It's just pairwise additive. It's weird. It's hyper incoherent, you might say. Okay. And then there's now relative likelihood is simpler, at least in terms of framework, because of how it's constructed. It'll always give you a possibilistic result. but possibilistic result on a binary space is kind of clunky. So whatever. So let's see what that looks like. Now, what you're looking at here, these are not cumulative distributions or C boxes or P boxes or anything. This is not that. This is a chart of how much belief and plausibility gets assigned to the proposition that interests you as a function of the results you got. So for simplicity, as a very simple example, we're going to do normal inference. We're interested in the value of theta, given that x is just a normal variate with, mean theta and variance 1. Okay, and we're just doing one sample, real simple. Okay, and these charts show, given the value of x, here's how much confidence or plausibility gets assigned to A. And if we're using that likelihood ratio, again, belief and plausibility are equal to each other, and it looks like this. Relative likelihood gives you a possibilistic structure, but you'll notice it mirrors the original structure. And I think these results are pretty intuitive as x. The nice thing about this problem is that x and theta are kind of equivalent. If x is close to theta, to a given value of theta, then that value of theta should be, kind of plausible. So you'll notice, like, when x is at 0, so the set we're interested in is A greater than 0, and when x is close to 0, it's 50-50 in the pairwise additive terms. And of course, as x goes up, you get more and more certain that A, that theta is greater than 0. Yeah. This is pretty boring. It's meant to be boring, this part of it. And just for reference, the likelihood ratio result is identical to what you'll get using Bayesian inference with a flat prior. Okay, which isn't too surprising. This is all very, maybe it's definitely surprising that the pairwise additivity of the likelihood ratio result was a little surprising to me way back when. But aside from that, it's kind of not surprising, because when you're doing normal mean inference, all roads kind of lead to Rome, until you decide you're interested in a two-sided set instead of a one-sided set. Then all of a sudden, all roads do not lead to Rome. And also we get some very counterintuitive results. Okay, so just a minute. All right, so let's say instead of being interested in whether or not theta is greater than 0, let's say we're interested in whether or not theta is part of a very small set, 0 to 0.1. That's very small compared to the variability of x. So we've got the same kind of chart we had before, where we're looking at the belief and plausibility assigned to this little interval as a function of x. And I think something's kind of weird here, where I think is a little weird, personally, that you would ever get a high assignment of belief to this interval. That you would ever get a high assignment of belief to it, because, your uncertainty is much bigger than that interval, But these are the results you get if you just plug and chug on these test statistics. If x is equal to 0, then or 0.05 rather, you'll be 100% certain that theta is in this little interval. Okay, so it's kind of like the reverse of what we had in the false confidence phenomenon. Now, for, I don't know, a few hours, I held out hope, maybe relative likelihood won't do this to us, because it's giving us possibilistic structures. But no, it still does it. Like, if you see, this gray line is the belief assignment. And you'll notice if x is in this narrow region, you're getting really high belief assignments of theta being equal to A over 0 point, sorry, being the interval from theta being in A. Let's just say that. All right, in this little tight, narrow interval. All right, so that's wrong. But let's also remember that the Bayesian answer is also wrong. What the Bayesian answer tells us is, you know, oh, and again, I don't mind having a low belief value, but it's also telling us that we have a very low plausibility that theta is ever in A. You know, no matter what value of X we get a very low plausibility assigned to this. So we're always very sure that theta is not an A. And if theta actually is an A, that's a problem. And this is really the simplest analogy, stripped down analogy that you can get to the satellite conjunction analysis problem, the collision analysis problem, where your set of interest really is a small set, but if it's in there, you want the data to show that it's plausible if it is. So okay. So what's going wrong here? Okay, so what was going wrong with the Bayesian solution is, of course, the false confidence phenomena, where you're guaranteed to think you're safe even if you're not. What's happening here is a little different, okay? Because if you think about it, if you think about sampling X a bunch of times, these really high assignments of belief to X, or sorry, to A, these really high assignments of belief to the proposition that theta is going to be in this narrow interval, those are wrong, like clearly wrong on their face, but they're only going to happen very rarely, okay? And that's actually kind of our clue into this whole thing. So like I've been insisting, if the uncertainty in your parameter is much bigger than the set you're analyzing, then you should never, that set should never get a high belief assignment. A high plausibility assignment, yeah, maybe if it, you know, if X is in that or near that set, but you shouldn't be getting a high belief assignment just intuitively. But that is just an intuition. How do we rationalize that intuition? And a few months ago, while I was doing laundry, it occurred to me that, well, the key to this whole thing is that the high assignment of belief is a fluke. So which is weird, and that's the reason why we're not really concerned about this thing as a safety issue, because it is a fluke. But also, that's the key to the counterintuition. You know, whatever the value of theta is, whatever the true value, whether A is true or false, you have a really low probability of getting that high assignment of belief to A. Okay, you know what I mean? Like that result is a fluke no matter what, and you know it's a fluke. So in that sense, that high assignment of belief is meta implausible, okay? Because you know it's a fluke either way. And like I said, this is a reversal of the false confidence phenomenon, you know? And the false confidence phenomenon, you know that, oh, I'm going to get a high assignment of belief. You say, oh, this is wrong because I was guaranteed to get this answer no matter what happened. This is the reverse of that. This is fluke confidence. Okay, in fluke confidence, we say this high assignment of belief is implausible because it's a fluke no matter what, you know, and I know that at the outset. And I want to emphasize that's not the case for when we're doing normal inference with a one-sided set, you know. If I get a high assignment of belief for theta being greater than 0, it's possible that, you know, if theta were much, much greater than 0, then it's possible I would have, you know, a very high probability of getting this high belief assignment. But in this case, where we're dealing with a narrow two-sided set, that no longer holds. You know, the values of X that would give you that high assignment of belief are very, very, like I said, very narrow range, and not highly probable no matter what the value of theta is. So, is there a workaround for this? I don't know what this is saying. Ah, whatever. Okay, sorry. Is there a workaround for this? And so far, what I found, so I don't have any definitive answers to this, okay? But I have, done some experimenting, and of course, one answer is, like the old joke, doctor, my arm hurts when I do this. Well, don't do that. In other words, just don't marginalize that hard. Don't pursue efficiency that doggedly. Don't go to the extent of like drilling into individual propositions. And what I found is a good kind of stopping point is what I call contour marginalization. So basically, let's stay in the world of confidence curves. Let's do marginal inference on a continuous variable. And if you want the most efficient inference for some particular proposition, then you should get a confidence curve for a, a marginal variable for which one value is the contour of the edge of the set that interests you. Okay, so, and this strategy works pretty well. This gets rid of the whole fluke confidence thing. So for example, if we just stuck with the confidence curve for mu, for normal inference, and we just did belief assignments for that, belief and plausibility assignments for that, to this narrow interval 0, 0.1, here's what that would look like. So again, the data are our x-axis, and the resulting belief assignment to A equals 0, 0.1, that's what we're seeing on the y-axis, the belief and plausibility assignments. Plausibility is on top in black, plausibility is gray on the bottom. And again, we get basically, I think, the behavior we want to see. As x gets close to A, it gets very plausible, but because A is narrow, much narrower than the variability of, x, we never get a lot of belief assigned to it. Now, in this case, now that's not contour marginalization. For this problem, contour marginalization would look something like getting the confidence curve for, say, mu minus 0.05 squared, okay? And as a special case, that includes 0 and 0.1. That's our contour for this one-dimensional set as a special case, Okay, so, and if you actually do that contour marginalization, you do get slightly tighter belief and plausibility assignments than you do just doing the confidence curve for mu. So again, this is not a confidence curve. These are belief and plausibility assignments for different results to that interval. But you'll notice you're getting lower plausibility, and at least where belief is possible, a higher belief assignment. What that does mean is, if you were to look at the confidence curves, they are tighter. So yeah. That's cool. Contour marginalization appears to work, but to really assess whether or not it works, we need an anchor. We need a benchmark. That's the word I'm looking for. And that brings up the case of, well, if we're worried about fluke confidence, or if we just don't want to deal with it, and period, is it maybe time for a second governing equation? This is how I think of things. I think of the validity criterion as kind of the first governing equation of statistical inference. And I'm going to throw out there, maybe we should have a second. That's, if you move things around, almost parallel. So one of the ways you can express the validity criterion, the Martin-Liu validity criterion, is that the plausibility you assign to any set, for any result x, should be greater than or equal to the probability of having gotten a lesser plausibility than the one you actually did. Okay, that puts a lower bound on how much plausibility is being assigned to a true hypothesis. That's the idea, which then is equivalent to limiting the belief that is assigned to a false hypothesis. So now we're saying, okay, that controls false confidence. What do we do to control fluke confidence? And I don't know if someone wants to suggest a different name, but I'm calling this the sensibility criterion, to keep us from getting belief assignments that we know are just on their face. We know it's wrong. We know it's a fluke. So here we're putting an upper bound on the belief function. And it's the probability that we get a higher plausibility than the one we actually did. Without going into a lot of details, it really does have to be, thank you, Viv. It really does have to be plausibility on the inside, not belief. And this has this, without going into why, if you dig into the math, this has kind of the side effect of almost requiring everything to be, if you enforce the sensibility criterion, it has a side effect of almost forcing you to do possibilistic math. And to me, that feels kind of like a cheat, but maybe Scott will remember an old story that our former mutual boss, Lev Ginsburg, used to tell, where the upshot is that the whole point of Axioms is, to get you the methodology you wanted. So maybe the fact that it feels like a cheat to me, it doesn't mean anything. Maybe that means I should be using it. I don't know. But anyway, here's, I've taken you through these 3 mini presentations about these real basic issues, but little weird things I've been dealing with for the past, I don't know, 2 or 3 years since I decided to dive into valid inference. Overall, my whole view is that statistical inference is this unfinished project. Statistical inference today is like physics before Isaac Newton. We don't have basic governing equations. We don't have anything. I mean, well, we do have one thing. We've got the validity criterion, and we've got a bunch of mathematical frameworks. We've got language, and that's not nothing. So at least from what we got done so far, I suspect we should have 2 more constraints. We should have some sort of loose likelihood conformity constraint. But again, there's a hard limit on how demanding you can get with that. And I think we should also have some sort of sensibility criterion. And this might be it, but I really want to emphasize this is all in its infancy, and I think we should be real careful about how quickly we commit to things. We should experiment a lot and commit very little. Because I think a lot of what makes the frequentist and Bayesian frameworks, let's say suboptimal. I think the meta problem with how they're developed is that people were in a real big damn hurry to kind of just suture it up and be like, aha, it's complete. This is a complete way to do inference. And, I think we should be a little more patient with ourselves than that. Now, one thing I've also been exploring is maybe we shouldn't be drilling down and committing to governing equation aside from validity. I think validity is rock solid. But instead of jumping and trying to say, okay, we should have this property and this property, instead, let's keep toying around and maybe see if there's like some quasi-likelihood test statistic that just kind of gives us intuitive inference, intuitive and efficient and intuitive and efficient and sensible inference, and then see what properties just come from that. And finally, not finally, there's one last point, but I really want to emphasize everything I've gone through in this presentation, the little spikes that you can sometimes get if you use the wrong test statistic, or hyperincoherence, or you know, these fluke confidence assignments. These are all counterintuitive, but that's all they are. None of this is world-ending. And I really want to emphasize false confidence that you get from using fully additive frameworks like confidence distributions or Bayesian posteriors or fiducial distributions. But really, Bayesian posteriors are the big thing, of course, because that's what everyone's using. False confidence is downright dangerous. And none of these problems are as bad as false confidence. And I really want to emphasize that point, because once these get out into publication, there are going to be people in the Bayesian camp who try to use these phenomena as like, oh, well, nobody should be, if they even pay attention, that is. People are going to use these phenomena as, you know, reasons like, oh, well, we shouldn't work with Bayesian framework. Look at these crazy problems. Well, I'd rather have these crazy problems than be guaranteed to get the wrong answer, you know, on some problems. So, you know, just a reminder of that. And then one last note, which stray thought, which I had the other night while writing this presentation, you know, the part about hyperincoherence specifically is, you know, do we even have the right mathematical language yet? You know, I'm still mostly working with possibility theory. I think for now that is the most operative framework for, you know, valid and efficient inference. But yeah, hyperincoherence really makes me wonder if there's some other mathematical language that would allow us to, you know, transcend these different marginalizations and have one representation that works for all of them. And if there is a better mathematical framework out there, it's up to us to find it. So yeah, that's the whole presentation, and I'm opening up the floor for questions.
Yeah, thank you. Yeah, so if you want to ask a question, you want to click on the raise hand option, and then I'll start picking on people, I guess. But yeah, thank you for your talk.
Yeah.
First question is Ryan.
Hey, Michael.
Hey.
Yeah, interesting presentation. Lots of crazy stuff. I like that. So I guess I had a couple questions. So I guess at the very beginning, I think you started out with this kind of bit about the I guess related to this coherence kind of idea, but I think it's this kind of the very first thing here. So I mean, the way I think about this is, so like any of these like possibility distributions, plausibility functions, whatever, they all have this monotonicity property. So like that thing that you have in the box is like, this is of course is guaranteed for plausibility, possibility. So I think what's going on here is more like you're changing the function.
Yeah.
So like when you do the marginalization, I think you kind of get to this, maybe it's on the next slide, where it's like, now there's this one thing that doesn't exist now.
Yes, this slide.
This different, like, yeah. So when you put this different subscript there, you're actually changing the function.
Yes.
And so then when you change the function itself, you can't expect it to be, you know, maintain these kind of like monotonicity properties.
Well, but I mean, you kind
not
of
really a question, but maybe it's more of like, I mean, I guess I wouldn't say that this is breaking coherence, at least in this sense, because the monotonicity property is still guaranteed. It's just what you've done is not, you've done an operation which is one that doesn't preserve these properties for all of the propositions.
Well, yeah, it's basically the function doesn't exist for some of those propositions.
Yeah, so I don't think that you could say that what you're doing is breaking like the monotonicity property, because it's like you're kind of comparing two functions. It's like apples and oranges type of thing, and so there's no sort of direct way to compare these things. So I don't know that I would say that it's a violation of that monotonicity property. It's more like you've just changed the function, so then they're not really comparable.
So I definitely think that's one way of looking at it, and it's definitely friendlier to our framework. The caveat I put on that, though, is that at least in the Bayesian framework, you do have, the plausibility subscript theta of B will be equal to plausibility subscript phi, of B, in the probabilistic framework. At least working in the Bayesian framework has kind of put this idea in our heads that, we should keep those properties across different marginalizations. I mean, do you think is that crazy? Or like, even if that's wrong, it might, like, I understand where that idea would come from. You know what I mean? Like that expectation.
I think it's that, they're not, I think where you're getting at here is you're arguing for like sharpening the inferences when you change the quantity of interest. So like, instead of having the full parameter of interest, you only care about some feature. And so you want the inference to kind of sharpen.
Yeah.
When you sort of narrow your focus, so you want the inference to sort of sharpen accordingly. And that's not a thing that that type of thought process doesn't go through the Bayesian mind. It's like you just get what you get. So the rules are defined and you get what you get. So here you have a different agenda. You're sort of trying to increase the efficiency when you marginalize. And so I think that's kind of the difference, is that here we're open to adjusting the rules to gain efficiency, whereas the Bayesians take the rules as given and then they get what they get.
Yeah, I'd say that's a good description. Yeah.
Okay, and then the last thing, I guess, or the second thing I wanted to ask about is towards the end of the presentation, you talked about the sensibility. I think that's what you called it, sensibility condition or criterion.
Yeah, and this is, I just want to preface, this is very, what's the word I'm looking for? Very tentative. Like, I'm not super committed to this yet.
Oh, sure. So I guess I had some thought about this. And so, the validity criterion, the way it's written here, is a little bit, I guess, different than I usually write it. But so here, if you think this thing with like the little x, if you treat that as like just a fixed quantity, say alpha, then this matches up exactly with the way it would normally be written. But I understand what you're trying to do here is say like any a and any x is basically the same as any alpha. So now if you look at the sensibility criterion, so now this is saying that, we want the belief to have some kind of upper bound. And so one way that you could see this happening actually is if the thing on the right side of your inequality, the supremum over a, blah, 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 if that was actually equal to plausibility of a given x.
I'm sorry, if it was equal to plausibility of a given x?
Sorry, so if in the, let's say, okay, let me say it a different way. If you had equality in the validity criterion above, and then you plug in that equality into the sensibility criterion below, then the condition actually turns out to be just that belief is less than plausibility.
Actually, it's not, because, and it's easy to miss.
Oh, you have the
signs are reversed.
Okay, so I guess what I was getting at was that, as kind of with the same kind of idea, there was this validity criteria, and then we thought, okay, well, we need to, validity is kind of a weak, I think it's necessary, but it's kind of a weak requirement. So if you said, well, what might you try to do to gain some efficiency, to sort of make sure that your inferences are sensible or reliable or something? What we thought about was actually to make this in the validity criterion, actually to try to force equality.
Well, that's for efficiency. Yeah.
So I guess I was wondering if there's I thought that it was a direct, sort of comparison, but maybe not. I missed this switch of the inequality down here. But so if this was equality in the validity criterion, does that say anything about sensibility here? Maybe not.
I don't think so. I'm not sure yet.
Sorry, I think I just jumped right to something I knew and I didn't pay some. I missed the swapping of this.
No, and it's okay, because I'm just throwing up this giant monster up here. Yeah, no, the idea, I guess I should just say what the idea of this sensibility criterion is, because I don't think I've explained it really, is that the belief we assign to a proposition should be bounded by the maximum possible probability of getting a more favorable result than the one we got. You know what I mean?
Yeah.
Yeah. So it is kind of a reverse of the p-value logic. And just because that's not the only, but the most direct way I can think of controlling for fluke confidence, because of course fluke confidence is where we're getting this high assignment of belief where we know you had a low probability of getting a result as favorable as that to the proposition in question, even if that proposition were true. It's weird. So yeah, the idea here is just that you're bounding it by that upper, what's the maximum, assuming that A is true, what's the maximum possible probability of getting a result as favorable as the one you actually got. That's the idea. So yeah, it reverses that sign in there.
One last thing, I guess, quick is so when I've done these things with like basically using these kind of structural equations and the random set, whereas your focus here kind of on the more like using the relative likelihood kind of things. So when I've done this with the structural equations and random sets, I've found that the belief tends to be small. Sometimes it's like especially if you have a really narrow type of hypothesis, like a proposition here, the belief would tend to be small. I don't think I've not noticed this this thing about X. You could have large belief. It might just be that I've not noticed it. Is there some difference between like this formulation with the likelihood, using like relative likelihood versus that kind of more structural equation approach?
I have not tried a structural equation approach to these problems yet, so I'd be very interested to see, if we did exactly this problem via the structural approach, I'd be very interested to see what results we got.
Okay.
But can you guess a framework where this also happens that we both recently wrote a response paper to?
Yeah.
Yeah. So for the rest of the group, this fluke confidence is built into confidence distributions in the work of like Hjort and Schwetter. We recently have been having an exchange with them. Ryan and I have, and also Scott now, where they're presenting their own solution to an analog to conjunction analysis, where they don't have the false confidence issue, but they are having fluke confidence. And because confidence distributions are designed basically to always be at least pairwise additive, you are going to have one or the other. You're going to have false confidence or you're going to have fluke confidence. You can't avoid it. Whereas, at least in a possibilistic framework, you do have at least the option of not marginalizing that hard and getting something that looks more sensible. So yeah, I really don't know what this looks like via the structural approach though. But if it doesn't have this issue, that's pretty cool.
Yeah, I guess I'm not sure. So I mean, it definitely would be worth to take a look. I think, at least in this example, should be easy. So
yeah,
it's worth checking out. Yeah.
Okay, cool.
Okay. Yeah, thanks a lot, Mike.
Let's follow up on that though.
Okay.
All right.
Okay, Adolphus, I think you have a question.
I'm having. Oh, sorry.
Yeah, Adolphus, we can't hear you. Are you?
Oh, can't hear me. Hear me now?
Yes.
All right. So actually, I was saying, yeah. So first of all, thank you so much, Michael, for the
the eye-opening, insightful discussion today. I think to be honest, I was kind of like mind blown and confused at the same time while at some of the parts. But I think it's a really like eye-opening to something like probably a new way of like interpreting all these intervals and whatnot. Okay, so I have two questions from this discussion today. So we just take one at a time. My first question is with regards to the slides where you talk about axioms versus efficiency. If we could go there.
Okay, axioms and efficiency, yes.
Yeah, axioms versus efficiency.
Yes, okay, here we go.
Yeah, so could you explain again the last point, like getting a plausibility of phi less than the plausibility of theta, therefore, could you explain that bit again?
Okay. Could you help me out? Give me just a sec. Okay. So I think this is better explained in picture form. So, okay. You remember the last presentation I gave where the whole point was we were doing these, we would build these joint structures on our original parameter space theta and then propagate them to some marginal variable that interests us. And then we'd go about trying to, basically beat down the plausibility distribution to make it tighter.
Yeah.
While still satisfying the validity criterion. Yeah. So this is basically the graph form of this first line. This line right here. This is what that looks like as a graph, basically.
Okay.
We're going from the black line to the blue line. Okay. So that's step one.
Sorry, remind me again, what's the blue one again, the blue line?
That's the efficient that's the efficient confidence curve on the marginal variable.
Right.
Okay. So the flip side of having a tighter structure is that our pointwise plausibility for all these, values of say mu1 over mu2 is lower than it was, just doing direct possibilistic marginalization. Okay.
Sure.
So if we then translate, so that's what it looks like on just the individual point values. If we translate that into measurable sets, this is a very stripped down diagram of what that looks like, Say we're interested in B, some two sets, A and B, And B, it corresponds to a range of values in our marginal variable. Whereas A is a subset of B, but it can't really be expressed in terms of the marginal variable. It's too specific. It includes information, about the other variables too, or it's constrained by the other variables too. So we can basically build this tighter structure for the marginal variable, which will cause the plausibility of B, because we squish down those pointwise plausibilities, that'll then show up in the measurable plausibility for B. And at least for certain A's within B, it'll be the case that the plausibility for B measured using our marginal structure will be less than the plausibility of A, which can only be measured using our original structure for the total parameter space. All right, and as Dr. Martin just pointed out, this is to a certain extent comparing apples and oranges, but the Bayesians have kind of accustomed us to expecting that changing variable isn't going to matter in an inferential context. And with pure aleatory uncertainty, it wouldn't, but this is not that. We're dealing with an inference. We're dealing with a very structured epistemic uncertainty. So sorry, your question. What is your question here?
No, it's just more of like just to clarify, like what exactly that you just explained for me in a pictorial form and this. So that's actually like the first question that I have. So like the second question that I have is
So wait,
regarding
did I answer your first question?
kind like sort of like
Kind
it,
of.
I sort of have a better idea now that we now that we look at the images and we look at this again and you explain with respect to the equation that you have beforehand, then it sort of like clarify things a bit. So
Okay.
thank you for that. And the second question I have is with regards to the inevitability, the slide on inevitability.
Okay.
Yeah, because I'm still a bit like very fuzzy about this like idea.
Okay. Well, it's whew, I do have the proof for this somewhere buried in my notes, but I may just have to rederive it. But basically, it all the whole ball game is basically. So do you want me to just go over why it's inevitable? Is that what you're asking, or?
Oh yeah, it's more of like why are we why is this like coming to the picture?
Okay.
Yeah.
Oh, okay. So basically, if you remember the validity criterion, that applies not just to measurable sets, but in effect, it will also apply to, point values of theta.
Mm-hmm.
So if you've got a valid structure on theta, then so two conditions. This becomes inevitable under two conditions, but those are also the two conditions where we care about inference. Okay, or sorry, where we care about efficient marginalization. Okay, so the first one, of course, is just validity. We care about validity. That's condition number one.
Mm-hmm.
And we've got a valid structure on theta. And condition number two is that the marginal variable we're interested in is a continuum of theta points. And I can't verbally express a proof because there's no amount of coffee that'll make that happen. But I can write it down. But I want you to kind of visualize the fact that, okay, imagine in theta space, you've got this string of points, this continuum of points that corresponds to this one value of your marginal variable, okay?
Mm-hmm.
And somewhere in that string of points is the true value of theta, okay?
Yeah.
But the whole string corresponds to the true value of your marginal variable.
All right.
Do you follow? Okay. So if you're to repeatedly draw different values of x, you'll get different, confidence curves. And if we're doing just straight possibilistic marginalization, then we're going across a whole string of values of theta, and we're saying, where's the maximum value of plausibility along that string of theta values, okay?
Right.
Okay, so, and this is the tough part that's to prove, but I'm gonna just ask you to take an intuitive leap with me, which is that it's an inevitability that in any given string, or it's a probabilistic inevitability. This is one of those with probability equal to 1, even though there's an infinitesimal chance of it happening. It's literally 0. There is no way that the maximum value of plausibility is going to occur at the true value, So we've got this whole string of theta values, and the true theta value is contained along that string. But with probability equal to 1, we can say that the highest plausibility is not going to occur at the true value of theta. You know what I mean?
Okay.
At least if we're dealing with a continuous observable. There's always going to be some value of theta, for every realized datum, there's going to be some value of theta along that string that has a higher plausibility value. Do you follow that much? Like there is an infinitesimal chance that we'll draw an X where the true value of that, but there's happen. along that string that has a higher plausibility.
Yes. Yeah. I'm with you on this part. So that
Oh,
probability, that probability of you drawing the most probable X is defined by the likelihood that you put into place, right?
mm-hmm.
Right.
I think so, if I'm following you correctly.
Like this you say this highest like possibility that you get the infinitesimal of X is defined by the likelihood function that you defined beforehand, right?
Uh-huh.
Okay.
Well, no. I just want to make sure we're talking about it. So you get that the string of theta values they correspond to one value of the marginal variable, right?
Right.
Okay. So then, what are you saying about the likelihood function?
Like, is it the one that dictates like which is the most plausible, like that you mentioned, that infinitesimal value?
Oh. I'm gonna say if I think I understand you, and the answer is not directly, but yes, indirectly, it affects that. Like yeah, I don't know, but let me just check. You're with me on the fact that for any given draw of the data, and any one confidence curve, that the maximum value of plausibility along that curve is not going to happen at the true theta value. You do get that part, right?
Yeah, that I follow you.
Okay, so then the second part is to have a valid inference on theta, the confidence curve has to be giving us a uniform plausibility. If we repeat samples, then the plausibility at the true theta value has to be have a uniform distribution over repeated samples of the data. You also get that, right?
Yeah.
So then, if you look at the value of, if you look at the plausibilities we're getting for the true marginal variable, the true value of the marginal variable, that's going to have a strictly right of uniform distribution. Because in every, because the true theta value, it has a uniform distribution. And for every result, the corresponding plausibility for the true marginal value will be, greater than that.
Okay.
Do you follow? So what that means is if we're doing direct possibilistic marginalization, we're going to have a structure on the marginal variable that is fatter than it needs to be, that is wider than it needs to be, that is more conservative than it needs to be. And there's going to be that potential to squish it down,
right?
By getting clever. And that's it. That's really the whole proof, because the incompatibilities that follow from squishing it down, that all just, that's all just a direct consequence of squishing it down. The real question is whether or not that potential always exists. And, within certain limits, within certain criteria for, the marginal variable as a function of theta, it does. It always happens.
Sure.
Okay, but so does that make sense?
Like, I have like a much slightly clearer idea as to what this is, but if it's possible, could I contact you to get if you have the proofs at some point in time, then maybe if I look at the proof, I might be able to understand.
Yeah, and I'll dig it up, and if I can't dig it up and someone wants to help me with the proof, that's good too. That's welcome too. But yeah, the real tough part of the proof, I remember being that part where you need to prove that there's always a greater, for each confidence curve, there's always a greater, more plausible value of theta along that filament. Yeah. That's the tough part, as I recall. And I don't remember how to do it. So I'm gonna dig through my notes, and because I'm gonna try to write each of these 3 little mini presentations, I'm gonna try to write them up as separate papers within the next month or 2.
Right.
So yes, I'd love to correspond with you about this, because it's cool. It's
sure.
cool.
Yeah, I could just contact you after this. just to like ask for it.
Sure. Sure, sounds good, but I will have to dig. Like, I'm not gonna have it.
Yeah, no rush, no rush.
Yeah.
Like, but yes, thank you so much for the explanation.
Sure. Absolutely.
Michael, could I ask you? I can't raise my hand, so I'm not being terribly impolite.
Okay.
If you go back to the previous slide, I mean, I just want to press Ryan's question really a little bit. It seems to me that this hyperincoherence does not actually constitute incoherence, does it? I mean,
I mean, certainly in a Bayesian sense, it does.
well, the Bayesians, you said they lead you to believe that it does, but I mean, you know, the inexistence of the quantity sort of prevents you from making the comparison of apples and apples, doesn't it? I guess I'm wondering.
Yeah.
How would Bayesian really be? Would they even notice this? And is it something they're going to get on their hind legs about?
So, if so there are two answers to that question. So, assuming I assume the Bayesians are going to keep ignoring us for at least another few years, just entirely ignoring us. But once they decide they can't ignore us anymore, yes, they're going to notice this. Yes, they're 100% going to notice this. And this is going to be something they latch onto, I guarantee it. But right now, they're still in the pretending we don't exist phase.
Right, but is it technically an incoherence? I mean, it doesn't, I don't think it violates Kolmogorov in any sense.
Oh, it absolutely does. Because, well,
How can it? It's just apples and oranges. There's no sense in which the same function is doing the bad thing. And you know, if you're marginalizing, you're doing some transformation. There shouldn't be. I don't think there should be a guarantee about.
Well, no. But in Bayesian world, this guy that I'm circling now, plausibility of B under theta, is equal to plausibility of phi under. Plausibility of B under phi. You know what I mean? Those two are equal. Transformation isn't supposed to change anything in the Bayesian world.
Well, but they make a lot of pretense like that. This is a different.
Sure, but that's I'm just saying it's a thing they're going to raise
what's the non-intuitive part of this? I guess I would ask.
I mean, no, I think it's just the intuition we have from being able to take this guy being equal to this guy. It's the detritus of having taken that for granted.
But I don't think that's an intuition so much as just a familiarity. It's just something you get used to maybe, but it's not something that's has to be.
I agree. But I think if I were to disagree with that, we'd just be splitting hairs on, you know, whether familiarity is an intuition.
Yeah, okay.
Yeah. Yeah, so
what I'm saying is it doesn't violate anything that I think any of us, even Bayesians, would hold as dear. I mean,
well, but there is kind of I guess you could say, inconsistency in that.
Surprise, for sure. It's a surprise, for sure, but it's not something that means, oh my God, you know, I'm doing it wrong. And maybe I'm being, you know, picky here too, but I guess I can imagine a lot of Bayesians saying, what's the big deal?
Oh, I can't, but maybe.
Okay.
I really think this is going to be one of their avenues of attack, but maybe I'm totally wrong. I think the amount of plausibility being assigned to B, depending on the framework in which you're viewing B, I think that's going to be a real bugaboo for at least some folks out there. You know, because it's the same data, it's the same proposition, but we're getting different answers depending on the
on what
different propositions. Yeah, I mean, well, think about it this way: Bayesians insist that stopping rules shouldn't matter, right?
Right.
Because of the likelihood principle. If they don't think stopping rules should matter, they're really going to think, you know, oh, the set of propositions you considered shouldn't matter.
Right.
Like if they got a gripe with
And
stopping
they
rules,
really do think that. You're right about that, of course.
yeah.
But they also don't believe that, well, I guess, posterior corrections of probability are necessary. You can ask all the questions you like.
Yeah. I don't know. Ryan, did you have a thought on this, or?
I guess I just I think I'm kind of on Scott's page. I don't know how the Bayesian would run into this, because
As long as you don't tell them.
well, I mean, ultimately you have the posterior on theta space, you do whatever marginalization you need, and you calculate probabilities, expectations, whatever. And so this would never show up to them. So I'm not sure. I mean, it doesn't really change the propositions don't change. I mean, you just follow the rules and everything, and you won't see this violation. So the only reason you're getting this violation is because you're not following the usual marginalization rules. So then you're trying to cheat and gain some efficiency. And so that by changing this function, by swapping those subscripts, you change the function, and now that's the part, and you've done that only because you want to try to gain efficiency on this margin.
Yeah, or the stripped down way to say it is, the only reason I'm noticing this is because I'm looking at both functions at once. Is I'm considering the structure for theta, and I'm considering the structure for the marginal variable. I'm looking at them both and being like, oh, these don't match up, and they don't match up on purpose. But yeah, you're right. If someone were just follow the rules and be like, aha, I've got a, suppose 10 years from now we had like the perfect, quasi likelihood test statistic for every situation that you can apply directly to some marginal variable. And you just go directly get your marginal inference. Then you're right, you'd never see this. But it is also worth remembering there are other situations where you do want to look at the original parameter, the structure from the original parameter space, rather than the most efficient thing for your marginal parameter space, like, data mining, where you're looking at a whole bunch of factors all at once, and you'd be like, which of these is statistically significant? In that case, you actually want to use the original structure for theta, because any marginal variable you'll be interested in, that interest will be informed by the result you got, and that'll poison your reliability claims.
So this actually reminds me of something. I don't think it's exactly the same, but it does remind me of, so there's a paper about marginalization paradoxes. This is a Phil David and I forget the first name, Stone, and then another is ZDAC. So this is in the JRSSB. It's like in the 70s. And so they talk about this marginalization paradoxes. And so I think at a kind of a high level, the way I would kind of summarize this one, if I remember correctly, is that they're kind of looking at different ways in which you could get the posterior for a marginal variable. And so one of them is to sort of directly take all the data in the model and then do the integration to marginalize.
Mm-hmm.
And another one was, well, you could only look at like part of the data or some summary of the data, and that summary of the data would have already canceled out the effect of some nuisance parameter. And then you build the Bayesian posterior through that kind of summary of the data. And that some kind of incompatibility between these two kinds of posterior distributions on the margin. And so this was actually a discussion paper, and there was some people thought that this was, sort of very strong support for one side, and other people thought that there was really nothing here. So it was kind of a controversial paper, but I guess whenever there's something about Bayesian marginalization paradoxes, it always goes back to that paper. So I don't know that it's exactly related to what you're saying, but I guess it was, this kind of incompatibility is something that I guess that reminded me of that paper. So maybe it's, I have it here somewhere, but I don't remember.
I'd like to take a look at this. This is because I've got another thing I've been working on since last week that's really basic, having to do with Bayesian inference and stopping rules, where you'll end up violating a really basic identity of Bayesian inference. I'll get to you. Anyway, with David and Stone, is that spelled with a W or a V?
Yeah, I don't know how to say it, so I say David because I don't know what else to say.
But it is with a W, right? Okay, just making sure.
Like David.
Hey, babe. D-A-W-I-D. How would you pronounce that?
I'm sorry, D-A-W-I-D?
Yeah, how would you pronounce that if it were Hebrew?
There is no W.
That's not a thing? Okay, never mind. Must be some other language.
Like the arrow.
Oh, maybe. Anyway, sorry. I was checking in for pronunciation, but no help there. It's not what I thought it was. Okay.
So, Michael, Daniel Kapalik had a question, and he and Martin had, or Ryan rather, had an exchange in the chat. Daniel, if you're still on, do you want to articulate the question? Because I'm actually kind of concerned about this too.
Yeah, I have not been looking at the chat at all.
Maybe Daniel's not there. You stuck a knife in my heart when you said that P boxes are incoherent. I'm going,
Well, they're in the Bayesian rhetoric sense.
Yeah.
Sure.
So Daniel's on now. Yeah, go ahead, Daniel.
Oh.
We still can't hear you though.
Was it Welsh? I love a random W.
Is it better?
Yeah, there you go.
Yeah, sorry, no, it wasn't anything important. It was just something struck my head when we were equating coherence and Kolmogorov axioms. But I think it was just fluke in my head. And not important, sorry.
I mean, it is true that IP can be entirely coherent, right? I'm not sure.
Well, it can be. It was defined in Peter Wallis' book and
Sure.
even in Matthias' work on over provisions.
Sure.
Coherence is a definitist term, as Dr. Martin said. Yes. But
So,
no, it wasn't much of a question. I was just overheard something. And
Yeah, I mean, yeah, when we get down to it, saying something's coherent or incoherent is just a definitional term. It's a and it's a very rhetorically charged term that, was deployed deliberately by Bayesians to attack everything that's not, Bayesian back in the 70s and 60s.
But clearly you can have the imprecise methods be entirely coherent.
Well, we would call it coherent because it's got a mathematical framework. But
No. I mean in the technical sense of the word coherent. It's not
Avoid pure loss, like kind of thing.
Avoid pure loss.
Yeah.
And doesn't have the probabilities adding up to bigger than one.
Sure, you just have to posit different decision rules than are posited in like Savage or Finetti. And because the decision rules in Savage and Finetti are dumb, but so the way guys like Schaefer or Wally get around that is by saying, well, no, we can't be forced to make a bet every single time. There's some things where we just won't make a bet either way. That's my understanding of that expanded coherence definition.
So what your answer, Ryan, says, what's your answer saying?
I just said that, I mean, there is a notion of coherence in imprecise probabilities too. And so I think the point here is that this was kind of my first point when I was asking questions earlier, was that I don't think that this is really something about the properties of these fixed functions. It's about that in what Michael's doing is kind of thinking about changing the function. And so then you can't expect this kind of, these properties to be preserved and change the actual function. So, I mean, whatever kind of, whether it's, probabilities or possibility distributions or something, I mean, they have some properties. And so like this monotonicity that Michael's talking about is always satisfied by all of these kinds of things. That's like a very basic type of property. So whatever is causing this violation is not about the coherence or incoherence in terms of like the properties of these fixed functions. It has to be that he's changing the function. And there's no reason, I mean, that's perfectly fine, but I don't think it's, incoherence and coherence is a way to kind of describe the phenomenon here.
The problem, yeah, yeah.
So whatever name we want to put on it, though, there is something weird about the plausibility be changing, or maybe not weird, but something new, shall we say, about the plausibility of B changing depending on what set of variables we're considering. Like the data didn't change, the model didn't change, only the questions we ask of the model changed. That's all that changed, and that alone, you know, changed the plausibility assignment to B, and really to every, or almost every proposition that can be expressed in marginal space. And that's...
I think that this is an important point because, well, it's that I think in a Bayesian type of perspective, it's that there's one solution that can give you sort of one framework that will give you answers to all questions, and that those answers are in some, you know, quote, they're good. So I think what's going on here is that if you want to give good answers to questions about margins, you have to consider that in how you do the analysis. So you don't for free get answers on margins starting from a general framework. I think you always have to say, okay, this was a particular question I'm interested in on this margin, and then I take that into consideration when I build my solution.
Yeah.
And so maybe there's incoherence in that because you considered something other than like just building one kind of framework that answers all the questions.
Yeah.
But Ryan, that sounds like it should violate the you know, going into a cookbook then, right? We're not going to get cookbook answers if that's the case. Every problem is unique.
Yeah, I think that you always have to, I mean, well, okay, so you can get cookbook answers that will be inefficient on some margins.
Mm.
But if
or alternatively,
margin in mind, and then you want to get most efficient, that has to be part of the considerations. You can't expect to be efficient on every margin for free.
Mm.
Well, and I would just jump in and say, I think we're not there yet, but I think it may one day be possible to get cookbook solutions for any marginal that interests you. It's just that you're going to have a different recipe for each marginal variable. You know,
yeah, that's the same. I think the same thing I'm saying is that you would have to think about what is the margin that you care about, and then if there's a cookbook, then you just pick the cookbook for that margin you're interested in. But you would have to consider which margin you're interested in building the solution.
Yeah.
So I note that Nick Gray in the chat has suggested that the name DAWID is Welsh because they love to throw in a random W. And if it's Welsh, of course, then DAWID is pronounced Chinawithblats.
Yeah. Anyway, yeah, I really don't know, but I do want to emphasize, you know, the third part of this presentation where, you know, I did about a year and a half ago go real hard at, well, heck, we're doing special things for each marginalization. And this is actually following up on a comment that Fraser made on a paper like 40 years ago. If you're going to have something special for each marginal variable, then why not something special for each proposition, for each set that interests you? And, you know, that's how I ended up getting this stuff. So we do need some more limitations, that's all.
Michael, you're familiar with that paper by, I think it's Grove and Halpern, about conditionalization being perfectly natural in the Bayesian case, but actually not being natural at all in the imprecise case. Are you familiar with this paper?
Not at all. Tell me more.
Well, he says I don't remember what the derivation was, but apparently in the precise case, if you have a few axioms that define how conditionalization behaves, there's only one way to do it, and it's the way that conditionalization works. But because I hate conditionalization because of, you know, the whole probability dilation problem already, I'm sensitive to this. So they're suggesting that in the IP case, conditionalization doesn't even make sense, that we shouldn't be doing it it that way. It should be subsets, not conditionalized sets, I guess.
Interesting.
And I don't know, maybe conditionalization and marginalization just sound the same to me because they've got lots of syllables.
No, they're very different though.
But I guess what I'm suggesting is maybe it shouldn't be surprising that what seemed perfectly natural in the precise model doesn't actually make sense at all in the imprecise model.
Well, and that's kind of what I was getting at. I don't think we disagree on this point. I think it does actually kind of make sense. Fewer questions means you're not trying to spread the data as thinly.
Yeah.
I think we've got a common understanding on that. It may just be a little, should we be calling this hyperincoherence or something else?
Yeah.
Or what would we call it?
Well, it's
yeah. I've been I'm usually a publish everything kind of guy, although I'm slow to get around to it. But I've been deliberately holding back on publishing this because I didn't want to pull a Birnbaum. You know.
I don't know what that means.
Well, like Birnbaum's argument for the strong likelihood principle, and you know, Birnbaum was a frequentist, but then he did this thing that gave the Bayesians a huge weapon for decades. And it turns out it's not actually a great argument, the argument for the likelihood principle. But so Birnbaum started with conditionality and sufficiency, and from that got likelihood, the likelihood principle, which says things like stopping rules don't matter. And if you actually dig into the details of the argument, it's not a great argument. Bayesians super latched onto it because you know, it was really convenient for them.
Yeah.
I did not want to do the same thing. I don't want to make the same mistake of publishing something that just ends up doing nothing but make my life harder.
Yeah, making a target for yourself.
Yeah. But now it's a little different because it is a fundamental result. It tells us something that we do need to know about. You know, it's a very basic fact that we need to know, that this idea that you know, that these two guys are necessarily going to be unequal. You know, that my inference about a proposition is going to change depending on the constellation of questions I was asking. That's an important fact for us to know, just in our own development. So, you know, as things are getting more uncertain on the ground here in the US, I have decided I can't sit on this any longer.
Is it necessarily?
Yes, it is necessarily.
It arose from the quest for efficiency. I thought it arose from the quest for efficiency. If you're not under that quest, is it necessary?
Okay, that's true. But
because I'm happy, us engineers are happy with suboptimal answers as long as the buildings stay up.
There's limits. I'm telling you, this thing grows. This thing grows with dimensionality. As you have more and more inputs, the over-conservatism gets absolutely ridiculous and unworkable. Like, it'll be workable for civil engineers, but it won't be workable for anyone else. You know, civil engineers can just pour more concrete, but things are a little tighter for aerospace engineers.
Right.
Yeah, or even electrical engineers.
Oh, Daniel has his hand up. You should just jump in.
May I?
Sure, of course, yeah.
Yeah, I was just wondering about the A subset B thing.
Okay.
Yeah, 11. One thing that strikes me is that the B on the left side, the B on the right side.
Uh-huh.
So they are not the same B's. So how do
you mean?
Because they live on different spaces, don't they? One is in the vertical axis, and the other one is the whole plane. So it also depends how you actually, if you project the B on the vertical axis, or how do you actually create it so that you can plug it into the function.
Daniel, I wish I had sound effects. I would say dun dun dun.
I mean, I would definitely argue that those two B's live in different contexts, but I'm certainly accustomed to thinking of them as logically equivalent. That's an interesting thought.
That's what I was saying. You're changing the function by sort of changing the world that it lives on.
Yeah, and I mean, I guess it's always been part of frequentist inference that everything is very context dependent. You know, frequentist inference is inherently context dependent, and all scientific inference is, you know, somewhat local and context dependent. But this is, I do think, an extra layer of context dependence, and at least I'm used to.
So the function is different, the argument is different, and it's got questionable intuition to start with. So we're ganging up on you now.
Well, but like, like, I mean, the thing is, I don't want, like, I also don't view this phenomenon, I don't view this as a game stopper. You know what I mean? I also don't view it as a game stopper. So you're ganging up on me, but at the same time, I'm like, okay, fine. like this is not a point I'm looking to, you know, if my side of the argument is this is a big deal and we need to lose sleep over it, I'm not looking to win that argument. Because in my heart of hearts, I also don't think it's a big deal that we need to lose sleep over. But it is weird. It's still new to me. It's worth noting, I think. I don't know.
We're approaching our limit. We sort of say 2 hours for these things, and some of them have been, like Vladimir's been holding on with his skin of his teeth. Does anybody have any final questions before we wrap up with Michael?
Yeah.
If not, I'd like to say thanks very much, Michael. Thanks everyone for participating. If you have any questions, pepper Michael with incessant emails. That would be my suggestion.
Okay.
Even though that would be your idea of hell.
Yes. Michael can take it. He's young.
Yeah, and you know, I'm bored. The apocalypse is very boring. It's,
I'm about to send you a manuscript to proofread, Michael. So,
are you serious? What?
Me and Alex, who is away, have been working on this paper, and Scott suggested that you might like to read it.
Well, probably.
It's about what we call the sing plots.
Ooh, I do like those. Yes. Okay.
Okay,
However, it needs
Thanks very much, everyone.